Before we get started, just a little reminder that On Humans is now available not only as a podcast, but also in written form. So head to onhumans.substack.com to read breakdowns and analysis of each new conversation. And if you want to, you can get all of these straight to your inbox, fresh from the shelf. I hope that you enjoyed. But let's get this episode started. This is the On Humans podcast with your host, Ilari Mäkelä. Probably the single most famous image in the history of philosophy is that of Plato's cave. It's a bit of an odd image if you make it very clear in your mind, but it's basically a few people living inside a cave, being chained to stare at the wall. And on the wall they see all sorts of fascinating things happening. But other things that are happening on the wall are actually just shadows that are created by puppet masters behind them. Now one day, one of these people goes outside of the cave, sees that the real world is made of all these three-dimensional things, the light of the sun, which is what really creates the shadows. Goes back, tells people that what they've used to know as reality is nothing but a projection, a shadow of reality. Of course, this philosopher is ridiculed, and a lot of drama follows. This is the kind of idea that inspired Matrix, the film, where the whole world that people are used to looking at is but a computer simulation run by evil machines to keep humans occupied in their slumber. My guest today is a very serious scientist who believes that something like this is actually happening. No, there are no evil machines. There are no evil puppet masters. There's actually nothing evil in this story. But there's a lot of mathematics. There's a lot of cutting-edge physics. And in that sense, this is a very fascinating story. So my guest is Donald Hoffman, a very notable cognitive scientist, famous mostly for his book, The Case Against Reality. Hoffman's thinking starts from some pretty basic ideas. Perception simplifies the world a lot. A lot of information is lost. Our brains create icons for things. And this sounds all fair and good. I mean, think about color. Is the red flower really red? Perhaps not. It just has a certain kind of surface, reflecting light at certain frequencies. When those frequencies hit our eyes, our brains eventually create the sensation of color red. In a sense, of course, then, redness is inside our head. Most of us are quite happy to do this with colors. But why do we stop there? Why is redness inside our head, but the shape of the flower is really there in the world? The three-dimensional shape, the structure, etc. In a sense, what Hoffman is doing is taking that idea that we feel relatively comfortable with in terms of color and applying it across the board. And that ends up being a pretty mind-bending theory. The redness is inside my mind. Oh, the whole flower is in a sense inside my mind. Oh, my head, my brain, my neurons are inside my mind. But it is a fascinating theory, not only because it leads into some very exciting science, but also because, as we discuss in the second half of this conversation, it addresses directly one of the most fundamental mysteries in modern science and philosophy, the so-called hard problem of consciousness. Now, this harks back to episode 17 that I did with Bernardo Kastrup. That was titled, Could Mind Be More Fundamental Than Matter? And that turned out to be the single most popular episode on the show's history. The problem that we discussed with Kastrup is how can it be that our inner life, full of meaning and feeling, could emerge from something feelingless, meaningless, the atoms, the molecules, the neurons, which modern science tends to say that the world is made of. Well, Kastrup says that's the wrong question to ask, because for him, mind, the feelings and the meanings are somehow fundamental. And one way to look at what Hoffman is doing in his work and what our discussion is going to be about is an attempt to flesh that out in terms of what does it really mean? How can we accommodate that with the incredible success of physical sciences? It's a fascinating picture, and it's not necessarily the right picture, but I think it's worth taking an hour and do our best, taking it seriously. To help you do your best, I've included a lot of names, links, etc. in the show notes. And as always, do consider supporting the show. Do subscribe to it if you haven't done so. Do give it a nice review if you haven't done so yet. And if you do want to join the lovely group of people who are actually supporting me financially, do head to patreon.com/onhumans. I really, really thank you for you considering it. It makes a huge difference, and without that, I couldn't keep the show alive. Anyway, let's get the show started with Donald Hoffman. Professor Donald Hoffman, welcome to On Humans.
Thank you very much for inviting me. It's a pleasure to be here.
I think for me and for many people, probably the easiest way to understand the way that you came to think about perception is to think about computer interfaces. I've heard you say this. This was kind of for me the moment it clicked, is that there is a trash can icon on my desktop. In a sense, it's very real. I drag my dissertation to the trash can icon, and holy moly, it's very real. But on the other hand, there is nothing in the kind of underlying reality of the computer. There is no two-dimensional space where the document is on the left and the trash can is on the right. It's a very, very useful interface, but it is so far from what the reality is actually about. And you're saying that our perception of the world is a bit similar.
That's exactly right. And this is on evolutionary grounds. Evolution by natural selection entails that our sensory systems evolved to guide adaptive behavior, period. And in that sense, very much like your desktop interface. It's there to help you have adaptive behavior toward a very complicated thing, namely the millions of circuits inside your computer. That's an incredibly complicated thing. If you had to toggle voltages to write emails or take photos or whatever, it would never get done. So your interface is there as an adaptive guide to controlling your computer, even though you could be utterly ignorant about what's going on inside the computer.
So basically, there's two creatures that have to write a dissertation using a computer. One of them sees the reality of voltages, and the other one sees the interface. The one who sees the interface is going to do a lot better.
They're going to do a lot better. It's so hard to toggle because you have to toggle the voltages, millions of them, in a precise order. If you get it wrong at all, it's wrong. So the interface is actually there to allow you to not only to ignore the reality, but also to successfully control that reality. And that's what evolution with natural selection does. It shapes sensory systems such that they will guide adaptive behavior. But a lot of us intuitively feel that somehow seeing the truth is part of having an adaptive interface. Right? Surely it's more adaptive to see the truth than to not to see the truth. That seems the intuition. And that's where that user interface analogy comes to the rescue, I think. With the computer, seeing the truth is not going to help you. Toggling voltages is really, really hard. If you're playing a video game, like a Grand Theft Auto, and you have a nice little VR headset and a little steering wheel and gas pedal, and you can play the game with that, and there's some geek who actually, sees the circuits in the software and is toggling and trying to beat you. Well, good luck. So to play the game of life, evolution gave us a VR headset, and that's what space-time is. Space-time is a headset, and all the objects in space-time are objects that we render on the fly, just like in VR. In Grand Theft Auto, I look over to the right and I see a red Ferrari. Well, there's no red Ferrari in the supercomputer. If you looked inside, there's nothing like a Ferrari in the supercomputer. The Ferrari is rendered and perceived by me when I look over there, and as soon as I look somewhere else and say a green Mustang, then the red Ferrari is completely gone. My friend who's playing, if it's a multiplayer game, and I have a friend in Europe who's playing with me, maybe my friend will say, I still see the red Ferrari, but that's because my friend is seeing in her headset and rendering her red Ferrari, which is not the same as my red Ferrari, although they're coordinated by the software inside the computer.
I mean, this is all very, in a sense, this is very dramatic and fascinating. And for the more mathematically oriented one, you have a fair bit of work with their simulations. There is a proof suggesting that evolution would work this way. I don't want to get too deep into that because whenever there is a proof, there is a lot of technical assumptions. And I want to still work on the kind of pretty general, talk in the general level here. But at least anybody who says, well, that can't possibly be the case. Well, it certainly can be the case. But there is a way in which this, I can hear someone being like nodding and yeah, I mean, absolutely. The world is made of quantum fields. I had this lovely moment. I was back when I was doing my undergrad, I often had lunch with a friend from the physics department. He was actually a postdoc. But I once was like, come on, you're a physicist. Just tell me what the world is made of. Like, we try this all the time at the philosophy department. We get nowhere. And he was like, oh, it's easy. Excitations in fields. That was his kind of,
Right.
that's, it's as easy as that. Well, let's take his point of view. I mean, that the world is made of excitations in quantum fields. Yes, there is no table in the kind of strict sense. The world is much weirder, much more difficult. If I were to actually try to interact with the table and the coffee cup, knowing about what's happening with excitations in quantum fields, I would be as miserable with the game of life as someone who's trying to play Grand Theft Auto by looking at the voltages. But that's not actually a very radical claim. I mean, they would say that this is a dramatically simplified interface that we have, and indeed, we only see this very, very small spectrum, even on the electromagnetic spectrum, and so there's all of this kind of. I can hear people being, yeah. Of course, Professor Hoffman is right as far as this goes, but that's not so radical, and you do make a claim that is more radical. So what is the difference between just taking physics seriously in this kind of way and taking the whole package that you're offering?
Right. Well, actually, a subgroup of physicists called the high energy theoretical physicists are actually saying the same thing that I'm saying, which is, and the way they put it is, space-time is doomed. So David Gross, for example, in a 2005 paper says that space-time is doomed, and then quotes several other physicists. And since then, Nima Arkani Hamed, who's at the Institute for Advanced Study at Princeton, is saying quite loudly that space-time is doomed.
If I understand correctly, what they're saying is that the idea that this three-dimensional space plus time, which Einstein fused into a four-dimensional space-time, is almost certainly not the most fundamental reality.
Exactly right.
But there are people who say, yeah, okay, well, we get string theory, where you have, I don't know how many dimensions you have. But
right.
How close is it just to like go? Let's go a little bit deeper. We get some vibrating strings in more dimensions rather than this three dimension. Is that's not what you're saying? I know that's not what you're saying. So I'm just trying to get to the real, the real distinction.
Yeah, that space-time itself is just the wrong concept. And quantum fields inside space-time are actually a fairly crude hack. Computationally, and then this is coming out of the new. So what Nima and colleagues are finding are new structures utterly outside of space-time. So they're not like hidden dimensions curled up inside space-time, like we tend to think about the extra dimensions in string theory as curled up inside space-time, but they're so small we can't see them.
I see.
Whereas what when you say space-time is doomed, and you're getting new structures outside of space-time, these are not like curled up inside. No, space-time itself is utterly kaput, gone. There's something entirely outside of space-time, and space-time ends up being a trivial projection of these more fundamental things that are not curled up inside space-time. They're utterly outside of space-time.
Things By the way, at least in the beginning, I want to kind of keep this as much as possible on the level of possibility that rather than certainty. So just exploring kind of how well this view, how possible it is rather than how certainly true it is. But I do want to ask here, how many percentage of high energy physicists do you think would agree with the strong space-time is doomed claim versus a kind of, well, yeah, it's definitely, we need a little bit more funky dimensions or something, but we can still broadly come out of it with something recognizably similar to what we think at the moment of space-time?
I don't know what percentage, but I would say that David Gross has said this, who won the Nobel Prize for his work on quantum chromodynamics. Ed Witten has said this, who's one of the fathers of M theory, or the father of M theory. Nathan Seiberg, who's at the Institute for Advanced Study. Andrew Strominger, Nima Arkani Hamed.
So a serious list.
It's a I mean, these are professors at Harvard and Princeton.
Yeah.
And David Gross is at, I think, UC Santa Barbara.
And
But
for listeners, I don't worry, there will be, as always, a list of all the scholars we mentioned in the show notes. So if you didn't catch all of that in one go, don't worry.
right. So the percentage, but put it this way, in 1905, there was one guy that was saying that space and time were doomed, and that we had to have space time, and that was Einstein. And it didn't matter that he was just the only one.
Yeah, fair enough.
Right.
Yeah.
But here you have a whole chorus of brilliant physicists, and what they're able to do, by the way, is it's not just space time is doomed, but they found new structures beyond space time that let them predict so-called scattering processes. Like two gluons colliding and four gluons spraying out, or something like that. And they can actually compute those scattering amplitudes with the new mathematics that they're finding outside of space-time. If you do that using quantum field theory and standard quantum computations in quantum field theory, it's hundreds of pages of algebra. It's an incredible mess. You do that with the new structures that they found outside of space-time, it's 3 terms you can compute by hand.
This is like the amplituhedron?
Yeah, and what Nima and colleagues do is they actually show you formulas that they can compute outside of space-time that give you the right answers. And the answers are very, very simple. 3 terms, 4 terms, 5 terms, instead of millions of terms and hundreds of pages. So what we're realizing is, when you're working in space-time and quantum field theory, it's such the wrong framework. You've lost so much information that the mathematics becomes unnecessarily hard and complicated. So this is a hint that we're onto something. What these structures are about is a big mystery. So the amplituhedron and these decorated permutations, which are behind the amplituhedron, decorated permutations are permutations like shuffling cards, right? What's being permuted outside of space-time? What's going on out there? No one knows. It's
even saying out there is so confusing, because of course when we say there, all we can imagine is a space there.
No, I agree. So maybe a little help on that point is, if you think about space-time as just your VR headset, and when I say what's there outside of space-time, it's sort of like, so space-time is just a VR headset that I'm wearing, and the question is, what is outside that VR headset? That's how I think about it.
I mean, the Matrix fans will get very, very excited.
Love that. Yeah.
Okay, so when my question was, well, isn't all you're saying kind of just like what anyone who pauses to think about the fact that the world is made of some pretty funky physicist stuff and IC tables and chairs? What you're saying is that it's not the same as the standard version of that, but yeah, actually it is just the same version as the more kind of cutting edge, what physicists are saying, version of that, which is that.
It's saying that space and time themselves are not reality. They're not fundamental reality, and so therefore nothing inside space and time. No quantum fields inside space and time are the fundamental reality. No particles in the so the bosons, leptons, and quarks are the standard model of physics, which are excitations of the quantum fields of space-time. All of that is an artifact of the headset that we're wearing. There's not the deep reality. And so, to be very explicit, no particle, no photon, no electron, no quark has any definite value of position, momentum, or spin when it's not observed. None. That's well established.
And that's that is the mind-bending thing about quantum mechanics that I think makes people, even like myself, who really doesn't understand the mathematics, come back to it again and again and again, to any popularization of it, trying to be like, what is going on?
That's right.
There's another actually thing that I think less people might be aware of, which resonates so strongly with this idea of the interface, the computer interface, or the VR interface, which is something that I have to admit. I mean, I've spent a fair amount of time with popular physics, and I just cannot do the math, But I've done. I during COVID, I was in New Zealand. I was going. My My then girlfriend is a New Zealander, and so we spent a fair amount of time, 9 months, 8 months in New Zealand during the lockdown periods, which was wonderful. But when we went there, we were in a quarantine hotel for 2 weeks. It's one of the best 2 weeks of my life, honestly. It was so wonderful. Just my desk, just time to spend together, and with studying whatever I wanted. Nobody can even reach me because I'm on the other side of the world, so they're asleep when I'm up. It was a funny experience. But anyway, back to the point. I took a quantum mechanics course, which was this kind of, I can put it in the show notes for people who are interested. It was a really well designed quantum mechanics course on Coursera, which kind of tried to go through the mathematics with very simple mathematics. So it was kind of for people like me who know who can kind of follow super simple math. So it wasn't just words, but it was not complicated maths, and it was really useful. And I watched a lot of Sean Carroll's Biggest Ideas in the Universe videos, which is a similar idea. Like, he does use math, but the most simple math possible, to kind of try to find the middle ground between pure words and math that loses 99% of the world population, maybe.
Sure.
And so I'm not coming at this from like, I didn't know anything, of what's going on. I've really tried, but it's so difficult to penetrate this without the math. But I didn't know that there is a thing called the Planck length and Planck time, which is an incredibly small kind of nugget or space-time. And below that, space-time doesn't make sense.
That's right.
That sounds like a pixel. That resonates so strongly with the idea of you zoom into the computer screen further and further and further and further. And at some point, you're like, wait, it doesn't make sense anymore. This is just, it doesn't, what's going on? And that is very textbook stuff. So can you talk a little bit about that idea of there being this pixel size that we know of space-time?
Yeah, now that's a point that David Gross made in his 2005 paper when he was saying that space-time is doomed. He was saying that it has no operational meaning beyond the Planck scale, 10 to the minus 33 centimeters, 10 to the minus 43 seconds. And that might seem pretty small to most people.
I mean, it's very small.
From my point of view, it's, space-time falls apart at 10 to the minus 33 centimeters, not 10 to the minus 33 trillion centimeters, just 10 to the minus 33. It's a cheap headset. We got a real headset. And only 10 to the minus 43 seconds, not 10 to the minus 43 trillion seconds, just 10 to the minus 43. So,
okay, fair enough. Yeah.
3 dimensions of space, 1 dimension of time. Seems like we got the low quality, cheap model. So space-time, in some sense, we're maybe over-impressed with space-time. I think I'm completely underwhelmed with it. I can imagine, from the point of view of evolution, by natural selection, right, for evolving headsets that are much more interesting. There's no principle why we couldn't imagine, have a 4-dimensional space, right? Right now, I can imagine a 3-dimensional cube, but if I try to imagine a 4-dimensional sphere or a 4-dimensional cube, nothing happens, right? Well, I felt cheated. I want a refund. I want a better model. I want a better headset. So
that's really funny. I want to get back to the physics towards the end, because you have some really kind of mind-bending suggestions on how to rethink physics from the deep end of the pool that we are still kind of on the shallow end of in this discussion. So let's get to that, but bracket physics for a while and maybe think a little bit more about just conceptually. I mean, a couple of clarifications. One thing is that one of the ideas that people, I think, are quite familiar with, one of my really good friends back also during my undergrad, not this time, not a physicist, this time a mathematician, gave me once a book. I think it was by, is it James Abbott or David Abbott? I can't quite remember now, called Flatland.
Flatland, right.
Do you happen to remember the name of the author?
It's Abbott, but I forget the...
Yeah, anyway, the story of a 2-dimensional space where objects move, they're rectangles and triangles and whatever. And they couldn't believe the idea that there's a 3-dimensional space out there. And it's really well told. If I get it right, you're actually saying something a little bit more radical than the idea that there's kind of an extra dimension from where we are projections of. You're really saying that it goes even deeper than that, right?
That's exactly right. And that's what, by the way, it's not just me, it's the high energy theoretical physicists like Nima and others who are saying that we're looking for structures entirely outside of space-time.
Yeah,
And
not just
entirely
a bit
outside
more
of time period.
complicated space. Yeah.
Right.
Yeah.
So that's, it's not just extra dimensions of space and
Yeah.
time
Yeah.
and so
Yeah.
forth. It's entire, and by the way, it's not just letting go of space time, but also letting go of quantum theory and quantum field theory.
Not
So
letting go of it, but seeing it as a special case of a more fundamental theory, right?
that's right. Letting go of it as the fundamental,
Yeah. Yeah.
as being
Yeah.
fundamental, and seeing it as derivative, as a
Yes.
projection of something far deeper. So space
Yeah.
time and quantum theory will emerge together from a
Yes. Yes.
far
Yes.
deeper mathematical framework.
Yeah, it is fascinating. I mean, I think I've been a Kantian, I think, for 12 years about reality. And it wasn't because I read Kant. I don't think, I mean, I think there are many 18-year-olds who are smarter than me and who can actually read and understand Kant. But for me, it was the high school textbook version of Kant. And I kind of realized it afterwards. I remember when I turned, it was really when I turned 18, it was my 18th birthday. And I was really into philosophy. I was going to apply to study theoretical philosophy at the University of Helsinki that spring. And I had this, I remember this sudden realization where it wasn't a realization because, of course, I might have been dead wrong. I might still be dead wrong. But I had this, it was inspired by something completely almost nonsensical in this context. I was at the Helsinki Design Museum with my parents. And there was this very famous quote, "Form follows function," just written on the wall. And I remember somehow my 18-year-old brain looking at that quote and thinking about the idea that if there would be no mentality, nothing kind of trying to find function in the world, I just don't know if there would be forms. I don't know if this thing that we look as three-dimensional forms would exist without there being this kind of mind constructing it somehow. And when I later learned about Kant, I was like, oh yeah, that's kind of exactly what I thought. And it was very kind of this kind of very unstructured, creative young brain just concocting ideas in a way that I didn't really have any argument for it. I was just like, yeah, I think that's how it goes. But Kant has been quite kind of special to me in that way. It sounds quite similar to what you're saying, because Kant says that there is the Ding an sich, there is the reality as it is. We can't know about it. What we have is we have these structures like space, time, causality, these things that we kind of concoct the reality to fit into those categories. Our mind does it. And that's kind of all we can ever know. For those who are not so deep in physics, but might have a more philosophical background and have read Kant, how much is this a kind of mathematical 21st century Immanuel Kant rephrase versus how much is it just is it actually a superficial similarity and you're saying something very different?
Well, it's similar. He has the distinction between the noumena and the phenomena.
Yeah.
And
the noumena being the things as such.
That's right. And the phenomena being our perceived world.
Yeah, yeah.
And so I'm making a similar kind of distinction. He said that we could say nothing intelligible about what was beyond the phenomena, and physicists are bravely going out there and writing down mathematical models.
Yes, I see. Yeah.
So and I'm also doing that. So I disagree with, Kant might be right. Maybe we will find that we can't do it, but we're going to go down trying. So one thing we're empirically disagree. I mean, in terms of what we're doing, we don't say that that you can't start to talk about the noumena. We're trying to build mathematical models of it and scientific models of what's outside the phenomena of space-time. So at the top philosophical level, yeah, I'm in broad agreement, but where we disagree is, of course, pretty critical.
Yeah.
And if I really said there's nothing I could do about the noumena, I wouldn't be doing any of the research I'm doing.
Yeah.
So,
I mean,
so there
Kant's conclusion was that therefore we continue doing science about the phenomena, and zero problem. We also have faith in God, in the noumena. And this is a beautiful solution for him because he doesn't need to be bothered about science anymore, and nobody can prove God, which he detested the idea of, because then there is no faith.
well,
um,
and Kant might be right, and I might be wrong.
huh,
Who knows? I'm just saying that
yeah.
for better or for worse, we're trying to at least take some. Now, what might be the case is that we can take a few steps out of the headset, out of the space-time headset. But maybe Kant is in some sense ultimately right in that we would never, and on this point, I would agree with him. We never are going to have a theory of everything. It's the very nature of scientific theories that they make assumptions,
Hmm.
and those are the miracles of that scientific theory. Are its assumptions, and there's no scientific theory that doesn't start with assumptions. So in that sense, yeah, Kant is absolutely right. We'll never have a theory of everything. And by the way, it's good because that gives an infinite job security to science.
Yeah.
Right? It means there's the next generation will always have the task of
Yeah.
bettering the theories that they receive from their seniors.
Yeah.
So we'll always be working towards better theory, but we certainly can have theories that go beyond our current phenomena. So there I disagree with him. So we can go beyond our current phenomena. Ultimately, we're going to have to test our theories in the only place we can test them, which is experiments in our phenomenal realm where we can actually experience them. But we can have theories of structures beyond our phenomena. But I would probably agree with Kant then that in some ultimate sense, we can never get the theory of the noumena fully. There is a deep fundamental mystery at the heart of everything.
Okay, well, now that we are in the kind of business of contrasting your view with first string theory and Kant, and maybe we should quickly just highlight that some people might get a kind of aha. This sounds a little bit like the simulation argument that we might be living inside a computer simulation. But you're saying something actually really different, right, from the kind of classic simulation argument by Nick Bostrom, because what he believes is that there is a base material space-time reality, that's the real deal. But we only live inside a program, which is kind of less real than that base bulky reality with desks and computers. But you're saying kind of something is almost the other way around. It's like any reality where you really have desks and laptops on it is part of the non-base reality.
Exactly right. So
Okay.
yeah, Bostrom and similar versions of the simulation theory say that what we're experiencing right now is just a simulation from some smart hacker on their little laptop somewhere. But
Yeah.
that hacker and their laptop are part of a simulation at an even deeper level. And at that base level, though, they think of it in terms of a physicalist space-time. And some real space-time hacker
Yeah.
in three dimensions of space and one dimension of time or whatever, so string theory world, whatever it might be. So I'm saying, no, you're not thinking outside of the box enough.
Yeah.
Any space-time for the base is that you're still in a VR headset. That's But they make another difference, another claim that's different from what I'm claiming. They're saying that my conscious experiences right now, my headache, my taste of chocolate, all of those conscious experiences are due to a program. Somehow a program is creating those conscious experiences. And there's not a shred of theory that supports this in the following sense. There is no theory that any of my colleagues, and I good friends with many colleagues who are working on physicalist theories of conscious experiences, so integrated information theory, global workspace theory, work theory, collapse of quantum microtubule states, and so forth, attentional schema theory. They're all the brilliant colleagues and friends who are working on these theories, trying to show how physical systems with the right kinds of computational structures or whatever functional structures can somehow give rise to conscious experiences. And here's the state of play. Pick any specific conscious experience that you want. Taste of chocolate, smell of garlic, sound of a trumpet, and ask any of these theorists, can your theory give me any, what specific conscious experience can you account for? And the answer is none.
It
There
is
is
actually
no proof.
striking when you put it that way, because the hard problem of consciousness is so often couched in a kind of generalized language, like how could any state be conscious?
Right,
To which it's so easy to say, well, give us some time, like we'll figure it out. But
right,
when
right.
you put it like we've had a few decades of really hard attempts, and there is not a single theory which is even close to explaining a single individual conscious experience. And I guess just to make it clear, do I understand it right? What you mean is that, let's say, the classic example from neuroscience, the V4 cortex and color vision. We simulate the V4 cortex, we experience color. Why is it necessary, based on my theory, that when it's the left bit of the V4, it's blue, and when it's the right, it's red? And it has to be. It could never have been the other way around. That would be an actually physicalist theory of color experience, and that there is not a single instance of anything like this being even suggested to be anywhere in the near distance. And when you put it like that, it is actually a striking failure. I don't know if you formulated it, or did you learn that formulation from others? Because I have heard very senior people like Philip Goff, very, very senior philosopher of mind, say that he has borrowed that argument from you.
I don't
Did
remember
you get it
reading
from
it
someone?
anywhere, so I just don't remember someone making that specific claim
Yeah, because it is a
immediately
very
after.
precise and scientific claim, in a sense that's we don't want to hand away the explanation of, oh, whenever you have integrated information. Yeah, and by the way, I love integrated information theory. I think that there are aspects of it are just fascinating and really revealing. But yeah, I mean, why is that bit of integrated information? Why does it have to be the taste of vanilla? And why can it absolutely not be the taste of chocolate? There isn't anything even remotely close.
There's nothing I actually asked Giulio Tononi this question. He came and visited the Helmholtz Club in the late 1990s at UC Irvine.
Yeah,
So he presented his theory then, and I asked him this question then, because it seemed to me the natural hard-nosed question to ask. And he had no examples. And I asked him a few years ago at a physics conference, and he said again he didn't have one. They've since published a paper on uh, their theory for space. So they have one paper where they're trying to say this is the IIT Q shape for space, and I'm in no way convinced.
but it is
So
an interesting development. Is that paper out already? Did you say, or is it
there's a
coming?
paper. There's a paper out, and
Okay.
I find it completely uncompelling. There's nothing on it that's compelling, but at least at least they're trying. And I should also say that the philosophers, um, for example, like Keith Frankish, who's a friend and a brilliant guy, and or Dan Dennett, who say that conscious experiences are illusions. So they're physicalists, and they're saying conscious experiences like a headache or a taste of chocolate, these are all illusions. You might say, okay, well, that's a good move because now that they're free of this problem that I'm putting
Yeah.
on. But no, they're not, because they have to explain what is the pattern of brain activity that must be the illusion of the
Yeah.
taste of chocolate and could
Yeah.
not be the illusion of green.
Yeah.
And so they have every bit of responsibility for a scientific theory ultimately, as the ones who say that conscious experiences are real. If you say it's an illusion, well, I have this illusion and not that illusion. As a scientist, I'm hard nosed. Give me a specific theory why this pattern of brain activity or integrated information must be the illusion of the taste of chocolate and could not
Yeah.
be the
Yeah. Yeah.
illusion of the.
Yeah.
So I mean, I'm interested in science. I'm not interested in hand waves. I have no interest at all in hand waves or one-upmanship. I want theories that work. And what's interesting is that my colleagues who are physicalists have chosen a research program for themselves in which they say, I assume that space and time and physical objects inside space and time and their functional properties are fundamental. And so they're fundamental. And if I also believe that conscious experiences exist, but are derivative from these, then I have to explain how these physical functional properties of physical systems give rise to the taste of chocolate, the smell of. So they have set themselves up that problem. Now, they don't have to choose that problem, but they've chosen to have that problem.
Yeah.
As Steve Pinker, when he likes the global workspace theory, and Pinker in his book Enlightenment Now in 2018 says he likes it, but he points out that it can't explain specific conscious experiences, and he says the connection may have to be stipulated. So the connection between this physical system, like some global workspace architecture or whatever it might be, or integrated information, and this specific conscious experience may be something that we have to just stipulate. So it's not really an explanation; it's a stipulation.
Yeah.
And I agree with Pinker. I
And
think
it's not one stipulation. It's not like, well, we just stipulate that there is something that it is. Because I used to think about probabilities. We just have to stipulate that there is something that it feels like to be a physical process. Okay, done. One stipulation. But you're very, very right. No, you have to do every single time. And this, we just stipulate that this feels like the taste of vanilla. And this,
there are millions of stipulations, millions of them.
yeah. It's not as easy as just one here.
We have a choice between physicalism, either the ones that say consciousness is real, or ones that say consciousness is an illusion. Either case, they're saying we're going to start with we assume space and time, we assume the standard model of physics, whatever it might be, we assume that, and we're going to also end up having to stipulate the conscious experiences or stipulate the connections with the illusions of. So we're going to stipulate those conscious experiences or the illusions. And I come back and I say, well, how about this? I will only stipulate the conscious experiences, and I will show how space and time arise from that. So I will stipulate less than you. I will only stipulate the conscious experiences outside of space-time and show that space-time arises as a headset inside this deeper theory. So let's take our theory of space-time itself, Einstein's theory and quantum theory, and ask ourselves, what do they tell us about space-time and the reality of space-time? And what they tell us is that space-time has no operational meaning past the Planck scale, right? They tell us that space-time is doomed.
Well, they don't exactly say space-time is doomed. I mean, I'm sure that there are people who are aware of the way that Planck scale work and says either something like, either adopt something like this, like string theory, or adopt something like, I mean, I don't know, for example, with like, just to get too technical, but like Roger Penrose's like twistor theory. I don't know how different it is from the way you approach it, but I mean, there's just so many theories in physics that I don't know, but I think it would be misleading to suggest that just the appreciation of Planck scale being this kind of pixel, I mean, it resonates with your theory, but I don't think it necessarily leads into just the only possible outcome.
Well, most physicists don't think this space-time is doomed. Most don't even realize that there are these physicists and high-energy theoretical physicists who say that. I was at a conference a little over a year ago where a number of quantum theorists, professional quantum theorists, were talking about their theories of consciousness. And at the end of each one, I asked them, what do you think about the research in high-energy theoretical physics that says that space-time is doomed? And to a person, they hadn't heard of it. And these are professional physicists. So this is a small group, but it's the group of theoretical physicists who are pushing the high energy limits of our current theories. They're the ones who actually, where the Planck scale matters, right?
Okay,
that's on the horizon. So for everyday, condensed matter physics and so forth, you don't have to worry about, space-time is doomed. You can continue if you're doing molecular, quantum molecular biology, whatever it might be. That's perfectly fine. It's only when you're at the theoretical edge of modern physics, you're saying what's beyond the standard model. It's the physicist you would expect to be facing this.
Okay, yeah. Well, can I ask you something? I mean, I really want to continue on the hard problem of consciousness. I think that's the reason this fascinates me so much, is the way you approach it. But I think in the kind of science philosophy podcast world, the in-house theoretical physicist is Sean Carroll, well earned by his amazing amount of internet presence, making these ideas somehow relatable to folks like me without a physics degree or even a proper grasp of the complicated mathematics. What would Sean Carroll say? Do you know what he would say?
I just interacted with him last Saturday.
Okay. Okay.
We both a conference in New York. So I spoke and Sean and I had some exchanges. So I think Sean is into the multiverse. And he's also thinks that decoherence can take care of the measurement problem in quantum theory, and my idea of conscious agents outside of space-time, he was not terribly excited about that at all.
Yeah.
He thought that there was the notion of emergent space-time. He said no big deal. Space-time is emergent.
Yeah, so he would say space-time is doomed if as a fundamental fabric of reality, but he just takes a very different turn after that. Is that right?
That's right. And he thinks that that multiverse will ultimately be the deeper theory outside of space-time in some sense.
I guess the reason I wanted to just get that out there is that I know that it is possible to be very convinced by your argument while not overselling it by saying that it is the only possible outcome of the theoretical physics. And I guess that Sean Carroll would be an example of someone who probably has taken relatively seriously the problems that you talk about. He would take a different turn, and therefore he will have a very, very difficult time with the hard problem, as you have defined it, described it.
Right.
And so that might be a reason to then take your turn. But I guess I just feel like a lot in the physics maybe resonates with this package that you're offering. It makes it very possible, but not necessarily determined like this is the only way we can go. I guess just to make the distinction was the reason. Sure. I wanted to press the point. Would you agree, or am I kind of selling the argument short?
I would completely agree with you, and I would say that at the best, if I'm really lucky, I'm taking a good next baby step. At the best, most likely I'm just flat wrong, but at the best, and that's the way science is that we're always taking the next baby step. Now, with Sean Carroll, I mean, I don't think that decoherence solves the measurement problem. That might be too technical for this conversation.
Yeah, it might be. Honestly, it might be. Yeah. But maybe if we can keep to the hard problem of consciousness.
Sure.
I mean, what you're suggesting is that we have this really serious problem, which is that nothing in what's happened in consciousness science suggests that we are even remotely close or have made any progress in solving the actual hard problem of consciousness. We get into this kind of generalist, oh, well, this kind of system is conscious, but why does this feel like red and not like green? I mean, the simplest question you could ever ask. We don't even have a way to start. And therefore you make a philosophical claim, okay, well, let's not try that. You have this whole story that we've already talked about why we shouldn't anyway try that, because neurons are objects or processes in space-time, and therefore not fundamental if they are part of the headset, part of the interface, not part of fundamental reality. But then you say, okay, well, what is part of fundamental reality? Are those experiences? And what you do is so difficult. Then the next step is so difficult, I think, for many people to understand, because you have a mathematical theory of how this works. And the idea that there is a mathematical theory, and I mean, I think immediately if we start talking about Markovian dynamics, we will lose everyone. So, I mean, not everyone, but me and a lot of the listeners. So without using the technical terminology of Markovian kernels and whatnot, can you just talk a little bit about how can we even start understanding what it means that you have a mathematical theory of how elementary conscious experiences combine to create a system which, as its projection, has space-time, and which also is so specific that you say that you can run simulations and predict fundamental physics, scattering amplitudes. But that to me, it sounds like this, I don't even know where to start.
Right. So first, just at top level without the mathematics, the way to think about the framework of what we're doing with consciousness is think about the Twitterverse, right? In the Twitterverse, there are millions of Twitter users, and, someone tweets and they have followers that receive the tweets, and then maybe forward, they might like the tweet and they might send it to somebody else. So there are millions of users and billions of tweets. If you wanted to really understand the Twitterverse, you could never read all the tweets or interact with all the users. It's just overwhelming, right? So it's this vast social network, and that's what I'm proposing. Reality is the vast social network of interacting, what we call conscious agents. But when you have a social network, there is a dynamics. You can talk about social network dynamics. How do pockets arise in which all these people have the same ideas. And over here, these people have these. So you get these stable configurations of ideas that propagate. And so you get propagations of patterns, and this image goes viral. Everybody sees it. This image only goes to this. So you can start to look at propagation through social networks. And it turns out that there's a very advanced mathematics of this. And the companies that are behind Twitter and Google and so forth are very, very sophisticated about the mathematics of social networks. And we're using that mathematics. We're saying, let's have these conscious agents, this social network, not inside space-time. We don't need it inside space-time. The mathematics does not require that they be embedded in space-time. They can just be an abstract network.
A platonic network of some element,
of agents that are exchanging experiences. Think about it probabilistically. If Hoffman gets this tweet, what's the probability that this kind of tweet he'll send off to his followers? What's the probability that he won't send the tweet off? So we published a proposal, and it actually won a little award from the Institute of Noetic Sciences back in June, where we're proposing to start with this theory of conscious agents and actually predict from our theory and match what high energy particle physicists have found when they look inside the structure of the proton. At the coarsest scale inside the proton, you see 3 quarks, 2 up quarks and a down quark. When you look a little bit higher spatial and temporal resolution, you see a quark C, quark-antiquark pairs that are pairing in gluon C. And when at the highest resolution of space and time that they've gotten, it's just a gluon C. These are the sort of the force carriers of the strong force. And what they get is momentum distributions. They can tell you, okay, at each resolution, how much of the momentum distribution is due to the 3 quarks? How much is it due to the C quarks? How much is due to the sea of the ocean of gluons? We're proposing to actually project our theory of conscious agent dynamics into space-time in such a way that we can actually get those exact momentum distributions to several decimal places.
But that sounds to me like a miracle if you can do it.
Here's how we've tried to pull off the miracle. We have to figure out the projection. So how do you project from a theory of conscious agents into space-time? And here the physicists gave us a big clue. The deepest structure, just in the last 10 years, they discovered the deepest structure they found outside of space-time are decorated permutations.
And by the way, if as a listener you don't know what that means, don't worry. Let's just keep listening. I don't know exactly what a decorated permutation is, but
it's a fancy way of talking about card shuffles, right? And why that's the deepest thing they found. Even the physicists are mystified, right? They're going, who ordered that? Who ordered decorated permutations as the deepest structure we found so far?
Okay, but go ahead. So given that card shuffle
is the deepest thing they found.
Is the deepest thing that we have quote unquote found, or a model that could explain the deepest things in a mathematically clean way. Given that, what's the next step?
So what the physicists do is they can take you from those decorated permutations into space-time and actually give you the exact scattering amplitudes for many processes.
Okay.
So we realized if we can connect to their decorated permutations, they do all the hard work of taking it into space-time. They've done that hard work. So what we asked ourselves a little over a year and a half ago, can we take our Markovian dynamics of conscious agents and project it into decorated permutations? If we can do that, then we'll go all the way into space-time because the physicists have done the rest. So we just asked, so have the mathematicians shown how to project Markov dynamics into decorated permutations? We did a search and they hadn't done it. So we did it. We figured out 2 different mathematical mappings. So it's 2 contributions to mathematics. So it was nice. We were forced to do some original mathematics and we projected our Markovian dynamics into decorated permutations. And then the physicists take us all the way into space-time and particle scattering. Now that we had that, we could then ask, what part of our Markovian dynamics of conscious agents corresponds to particles? We know what part of the decorated permutations map into particles. So we could then say, these are the units of our theory that correspond to particles. So we did that. They're called recurrent communicating classes. So the physicists helped us out. They pointed us, we discovered it's these recurrent communicating classes. So then we said, okay, then what corresponds to mass? And it turns out we could figure it's the entropy rate. What corresponds to momentum? It's the number of states in the recurrent communicating class. What corresponds?
Can I ask how surprised were you when you found this? Because given that I just cannot follow the mathematics, let's say that I mentioned before we started that I lived in China and had my time learning Chinese characters there. Now, let's say that somebody who, someone from Europe comes and starts studying Chinese, and they try to uncode the language, and then they find that there is a way to use Romanic alphabet,
right,
to fully capture every sound in Chinese language, which there is, which is the Hanyu pinyin. If I come and say, look, I can use the Roman alphabet to capture the whole of Chinese language. So actually, the Chinese language is a projection of the deeper linguistic reality, which is that the Romanic alphabet is like this fundamental power. I'm getting kind of off tracks there, because it's so not surprising. It's kind of almost trivially true that I can just map them onto sounds. I create the mapping, and so from a kind of, this is actually quite a trivial finding, the kind of Chinese using Roman alphabet, to, oh my God, this is actually incredible how surprising it is that there was this mapping. Where are we operating? Because I can judge.
We were stunned to discover that all the basic properties that we need to describe a physical particle were there in the recurrent communicating class. And it was so stunning. At this point, we were partway through this, and a particle physicist named Hoffman Chandopattier, who's an experimental particle physicist. He's a professor at UC Berkeley, but he works at CERN and Fermilab and he has for about 35 years, something like that, doing designing and building real particle experiments. When he saw what we were doing, he joined our team. And together, we put together this paper that won this little award from the Institute of Noetic Sciences. And to me, it's been a complete stunning experience that this was even possible.
Can you help me understand this reality then? This I don't know if it's Platonic reality, how should we call it? But this hidden reality of conscious agents, conscious experiences. I mean, what is there? Because you can have the mathematics. I mean, I think the common way to say is that, okay, you can have the mathematics, that what breathes fire into the equations, and you say that what breathes fire into the equations is somehow conscious experience. That's what is there. But I guess what I'm struggling with is that, let's say I'm looking at a new Apple product and it tingles my senses. It just sounds so incredibly human in a kind of trivializing sense, like, this is not a very profound thing. Given that the structure of the universe probably doesn't have one element in the same way as we used to think that it has up quarks and down quarks, it probably doesn't have like desire for Apple products and desire for Samsung products deep down there. But what is there that can make up this very uniquely human experience?
Well, it's a great question. So the mathematics that we have starts off with these little conscious agents that have only one experience, say, red, and we look at their interactions. We start to build up more complicated conscious, as big as we want. And we do that because that's what's feasible to do with, technical tools and mathematics. But that mathematics itself our mathematics tells us that approach is limited, because interacting conscious agents form new agents. And that means that we can have, if we start off with a countable infinity of conscious agents, we can get a higher level infinity of their combinations. We can take a bunch of them, have them interact. That combination is a new conscious agent. You get new levels of infinities. And so what we realize is our theory is telling us there's ultimately one big conscious agent, maybe. There's one. But you'd have to climb up all of Cantor's hierarchy and beyond to get to it. So we can't. But so our theory points to it and says you'll never get there. So right. So but that's what a good scientific theory does, right? A good scientific theory tells you its limits. So Einstein's theory of gravity says space-time is a wonderful structure until you get to the Planck scale, and that's the limit. Then it's gone. So a good scientific theory tells you the scope of the theory and the limits of the theory. And our limit is, our theory says looks like there's one agent, and everything is a projection of that one agent, and you will never model that one agent. But you can model these projections and projections of projections. That's what you can do, and you can make testable stuff there, but you'll never get to the one. So that's where I am right now. Now, the question is, what can we say about the one?
Well, Kant would want you to say absolutely nothing except that we have more maybe reason for faith.
and Kant might be right.
But please, I guess the reason I said that, I mean, half a joke, but half to just point out that is there's a deep spiritual potential.
Yes.
And if the term God comes to someone's mind, I don't think it's completely, ordinary.
Right. And I think that I have a lot of interaction now with people from spiritual traditions, because this part of the theory really sort of resonates with things they've been saying for thousands of years. And for what it's worth, my own guess right now is that you and I are the one, just using an avatar. So it's the one talking to itself through billions of human avatars and cat avatars and mouse avatars and tree and plant avatars. These are all just interfaces that the one is using to explore its potential. And I can't know the one in a conceptual sense, but I can know it directly because I am it. But now I've gone on that part. I've gone beyond my science. Where the science goes is all the finite collections of conscious agents and their properties and mapping into space-time. That's the science. This other part is me reading the tea leaves of the math and saying, this is, Hoffman's best guess.
Okay, that was it for today. As you might imagine, that's not the end of the conversation. We went on talking for another half an hour or so, but I decided to go with 2 different episodes. This is for 2 reasons. One is that, as Professor Hoffman mentions, this is where the science ends and the reading from the tea leaves begins. And I just wanted to make it crystal clear that that's separate. You can buy the science without the spirituality. You can buy the spirituality without the science. Another reason is that now that this is a lot to take in, a lot of details, a lot of new words, etc. And I thought that maybe giving a little refresher in the introduction to the next episode will also be helpful. And that will be out very soon, within the next week. Stay tuned. Until then, take care.